Okay, in this video, we're going to take the step away from just finding areas using integrals towards finding volume, this three-dimensional measure of size and space. So this is going to be a little bit different, but what we're going to do is we're going to try and use this slice and sum method to cut up our solids into some smaller pieces, find volumes on each of the pieces, and add them all together, and that should turn out an integral formula for us when we do this slice and sum method. So we'll talk about how to slice these things up. We'll talk about how to form a solid by revolving a region around an axis. These are called solids of revolution. They're going to be really important for us, mostly because they're going to be pretty consistent to work with then. And then there's two methods that we can use for finding volumes in this way that we're going to talk about in this video, disks and washers. So let's just start off with the basic idea of how to find a volume by slicing things. So again, we're going to take this slice and sum strategy. We have some sort of a three-dimensional solid. You can imagine like a ball or a cube or something else, whatever you would like. And we're going to try and slice this up into really small pieces. I always imagine taking a big bit of ham or something like that and running it through a deli slicer. What are those slices going to be? Well, they're going to be really, really thin. And then they're going to have some sort of a face. The face side of it is going to be some sort of a shape. So if we were cutting up some sort of a ham, all of our bits of ham are going to look like this, we'll say, and they're all going to be very thin slices. They don't have a lot of thickness to them. I'm not an artist, as you can see, so this isn't a very good picture, but we can try and imagine how we would find the volume of this. What we're going to do is we're going to imagine these as some sort of like prism type things. You can imagine like a small cylinder or a really, really thin rectangular prism. We have some sort of a thickness, and then we have an area of a face. And just like finding the volumes of any of these things, we need to know the area, and we need to know the thickness. So our slices are going to be different, but hopefully they're going to differ based on what the areas are of these different cross-sectional slices. Then we can think of how to construct our Riemann sums. Well, we'll look at the area of the kth slice. We're going to go ahead and add those all up. We'll need to find the volume of the kth slice. Sorry about that. But that volume is going to be the area times our thickness. There we go. A sub k is just the area of the kth slice times whatever thickness we use, and then we'll add those up. And use a limit. So let's go ahead and do this. The volume of the kth slice, well, we're going to hope to have some sort of a function to define the area. We'll call it a of x. And then we can say the volume of the kth slice is going to be a of x sub k star. That'll be the area of the face of that slice. And again, this is going to be dependent on some x value in a little subinterval. And we'll multiply it by a thickness, which we're going to call delta x. And then we can get an approximation by adding these all up. The total volume is approximately this sum from k equals 1 up to n slices of a of x sub k star delta x. And this looks like a Riemann sum, so we can say our volume is exactly the limit as n goes to infinity of this Riemann sum. And remember, by the magic of Riemann sums and the definition of the definite integral, this turns into an integral from some starting point a to an ending point b of the area function, dx. Our delta x turns into dx. We lose the x sub k star, and it just turns into x because now we're not electing some sort of x value from each subinterval to represent the whole thing. We're going to have these infinitely thin slices surrounding each x value. So here's our whole result. For some three-dimensional shape formed between x equals a and x equals b, if a of x is a function that represents the cross-sectional area at some point x, then there's our integral formula for the volume of the solid. This is going to be really huge for us because what this means is that we really just need to focus on the area of the face of these cross-sections. As we slice these up, we're going to try and figure out what kinds of shapes do we get. Sometimes we'll have to figure that out, but when we move towards solids of revolution, that's going to make things a little bit more consistent for us. So just like with Riemann sums where we were finding area under curves, we were assuming that all of our subintervals gave us rectangles and we had to know the height at each point of each rectangle. Now we're not going to have a two-dimensional rectangle, we'll have a three-dimensional little prism here, and we need to know the area of each of the cross sections, and then we'll multiply that by the thickness. So let's go ahead and take a look at some examples. I've already drawn some of these out because they can get kind of tricky. So imagine a solid whose base is the region bounded by the curve y equals 9 minus x squared. So that's what I've drawn in the first quadrant, and whose cross sections are squares. I tried to draw that, but I got a little rectangular. Oh well. So I went ahead and drew a red line here, and you can imagine that we're looking at this from above. So our shaded in region matches up with the base of this thing here. Hopefully that's helpful to see. And then you can see that red line crossing from our x-axis right here up. And then we call this thing here the y-axis. So I've kind of taken this picture, flipped it down, and tilted it so we can kind of see what's going on. So what we need are a couple of different things. We know that in general, our volume is going to be this integral from a to b of an area function. And we also know that my cross sections are squares. Areas of squares are super easy, right? We just need to know the length of one of the squares. So we'll have to take a look at our picture and see if we can figure out what the length of one side of the square is. And that's going to be noticeable right here. Because you'll notice that the y value at this point gives us the length. So this is our y value. It's 9 minus x squared. So when we draw our cross section, I always like to do this. Here's our little slice. Sometimes I'll draw this in 3 dimensions. Sometimes I'll just leave it as a 2-dimensional thing. I need to find the area of the face. I know that my thickness is going to be delta x, because really we have like a tiny little rectangle here. And so I'll say this side right there is delta x. And this side length right here was 9 minus x squared, but that means that this is 9 minus x squared as well, because we know that this shape here is a square. So I can find the volume of this slice really easily, right? I can say v sub k, the volume of the kth slice, is going to be 9 minus x squared squared. Now really it would be an x sub k star times delta x. But the main goal here is that we can find the area of this face by just saying our area function now is 9 minus x squared squared. And now we can integrate, and we can say the volume is going to be some integral of 9 minus x squared squared dx. We need limits of integration. These are going to be x values because they're going to be places where our rectangles, our slices, are stacked from and to. So we need an x value here. This is x equals 0. And we need an x value here. That's x equals 3. So we're going to go from 0 to 3. And now this integral is not a hard thing to do. We can multiply a little bit, and we'll have now the integral of 81 minus 18x squared plus x to the 4 dx. And this should be easy enough for us to do. I'm going to leave it here. We'll find that I rarely end up actually evaluating these integrals because we should be able to do that, right? Antiderivatives are pretty easy. Evaluating isn't that bad. Things should go pretty well. This is just a polynomial function, so I'll leave that for you. All right, let's think about this same thing, except we're going to change the shape of our cross sections. Now, instead of squares, we're going to have semicircles. So this is going to be a little bit different because it's going to change our area function. Here's our cross section. It's this semicircle with a little bit of thickness here. So you can kind of imagine like a half coin if you want. And the thickness, again, is delta x, because that's our thickness of this little rectangle right here. And then we have to figure out what the area of a semicircle is. Well, we know that the area of a semicircle is half of the area of a circle. So our area function is going to just be half of pi r squared. And we need to figure out what our radius is. The radius is this distance, meaning it's this distance, meaning it's half of this length. So our radius is going to be 9 minus x squared over 2. You could think that length that we found earlier, that was the length of the side of our square, that's the diameter of our semicircle, and we want the radius, so we have to look at half of that thing. So suddenly our integral again becomes not too bad. This is an integral again from 0 to 3. That part hasn't changed because we're still looking at that same base region. But now our area function is going to be half pi 9 minus x squared over 2 squared dx. What I might do is pull out my pi over 8, right? I'm going to have a denominator of 2 and a denominator of 2 squared. So I'll say this is pi over 8 times the integral from 0 to 3 of 9 minus x squared, which is again 81 minus 18x squared plus x to the 4 dx. And so we should be able to do that pretty easily as well. So all of this to say, these examples aren't too bad as long as we can visualize them. And that's, I think, the tricky part here, is making sure we can really understand what these surfaces look like, what these solids look like. We end up with really strange things when we just describe a solid by the shape of its base and the shape of its cross sections. So it's really easy to make a little bit of confusion get tossed in here and throw off the whole thing. Because of that, we rarely focus on these general solids. What we're going to do is focus on solids of revolution a little bit more carefully. Now, these solids of revolution are, in one sense, going to be a little bit trickier because there's going to be like a new hitch thrown in the visualization. But once we can see it, these are going to be much easier to deal with because they're going to give us some consistency for how these solids are built. Meaning it's going to take the guesswork out of having to sketch some base and then visualize some shape coming out of that base with these different cross-sectional things. It's tricky to do that. So these solids of revolution are going to give us a little bit of an easier time simply because there's going to be a consistent way that we form our three-dimensional solids. Here's the basic idea. We're going to create a three-dimensional solid in a formulaic way, just like I said. We're going to set up some function or functions to create a region, and then what we're going to do is we're going to spin that region around an axis and create a solid by looking at the shape it takes up as it spins. This is kind of a weird explanation, but take a look at this. We have this shape here, and now we're revolving it around the x-axis, and you can see it's actually creating some three-dimensional cup-like figure. I'll let this image run again. So I'll try and put things back into place, and here it's undoing the revolution. But we're going to be looking at this square root function, and we'll take a look at it a little bit more in depth in a second. And we start revolving it around the x-axis right now. And you can see that as our square root function turns around our x-axis, we create this kind of cup image. So this is going to be really nice once we get a handle on the visualization, because again, these solids are going to be formed in this consistent formulaic way. So that will be really, really helpful for us. So let's go ahead and take a look at that region that we were just looking at, that square root function, and we're going to revolve it around the x-axis. We want to find the volume of that solid we were just picturing. The first thing that we're going to do is use and define the disk method. So I've just drawn a general function here. This is not the function that we were looking at, but we want to set up the disk method in general. So I'm going to imagine some sort of rectangle on my function or on that region, and we're going to revolve that rectangle around the axis. What we really care about is getting this kind of a shape I'll see if I can draw it nicely. When we revolve this, we get this kind of vase-looking shape that sometimes can be tricky to draw, but hopefully we can see that, and our axis goes right through the middle this way, right? When we follow this little rectangle around, what that does is it creates this little circular cross-section. And then if you imagine plucking that little cross-section out, it just ends up looking something like this by itself. It's like a really thin coin. And if we flatten that, maybe I'll grab my little circle drawing shape so it does a better job of it for me. There we go. If we flatten that, then we end up with just a circle that has some sort of a thickness to it. Now the thickness is going to be delta x. That's right here. And then what we need is to find the area of this, and so we need a radius. That's going to give us the area of the face, because the area is again going to be pi r squared. The radius is this distance from the middle to the edge. So let me draw it on this one here. It's kind of tricky. There we go. We'll draw it on this one here as well. And you'll notice that if we draw that, that's right here. That's our radius. Our radius is the height of the rectangle that we drew originally. So our radius is just whatever our function is. Meaning the volume of the kth slice is going to be the area at x sub k star times delta x. The area, though, is going to be pi r squared. So this is going to be pi times f of x sub k star squared times delta x. There's our pi r squared for the area of our circle times the thickness. The total volume then can be approximated by the sum of all of these slices. You can imagine a whole bunch of rectangles stacked next to each other, a whole bunch of these weird little discs stacked on top of each other to create this vase or vase. And I guess not on top of each other, next to each other in this case. And so that's going to look like pi times f of x sub k star squared delta x. And then to get the actual volume, we're going to take a limit as n goes to infinity of this thing. And the beautiful part is that once we do that, we end up with an integral. This is the integral from a to b of pi times f of x squared dx. So this is our integral formula for volumes using disks. We call these things disks because they look like these little coin type things. Our cross sections, they're these little circular shapes with some thickness on here. So here we go. Here's the disk method for finding volume. As long as f is a continuous function that's non-negative, then we can go ahead and spin it around the x-axis, and the volume of that solid is this integral formula. You'll notice that here I factored the pi out. I do that a decent amount. I'll bring those little annoying coefficients out front. So we just worry about squaring our function. All right, in our last video, we talked about integrating with respect to y. And so we could imagine what's going to happen here. What if we revolve around the y-axis instead? So what if we have some sort of a shape that looks like this, whatever, and we look at it right here, and we revolve around our y-axis. Then what you'll notice is that our rectangles go this way, and so they have a little delta y instead. And you'll notice that our radius is going to be an x value, so we'll say it's f of y. And then from there on out, it goes the exact same. So we can say, in this case, our volume is going to be, I like to call it c and d, so we don't get them confused with the x values, a and b. This interval from c to d of pi of f of y squared dy. No big deal. All right, so let's go ahead and take a look at some examples here. So let me draw a picture of this region. we've got that square root function. This is the one that we were looking at in our little animation. Our square root function from 0 to 4. And this is the region that we've got. We're going to revolve it around the x-axis. I always like to draw at least one little rectangle on here, just to make sure I can get a sense for what this is going to look like. I can see that the small side of my rectangle is delta x. When I revolve that rectangle around, I'm going to end up with some sort of a little coin shape like this. From here, I can see my nice circular, I got to get my circle tool. I got to get used to doing that. There we go. My nice circular cross section where I need the radius, and we can see here the radius is equal to the square root of x. So my area is pi times the square root of x squared, which is not pi times x. It's technically pi times the absolute value of x. When we square it, we know we're going to get a positive value out of this. Now, that's not going to be a big deal for us, because notice our limits of integration are going to go from 0 to 4. So they are positive values. So what this means is that our volume ends up being an integral, pi times the integral from 0 to 4 of our radius squared, and that's going to be x dx. This is easy to anti-differentiate then. We have x squared over 2. We'll evaluate that from 0 to 4, and we end up with pi times 4 squared over 2 minus pi times 0 squared over 2, which gives us 16 pi over 2, or 8 pi. And that's the volume of this shape that we've got, this solid that we created. Here's another example. I'll help us sketch this thing out, but then I would encourage you to just pause our video and see if you can figure this one out. It's a little bit different. We're going to swap things around the y-axis now. I still have this same square root function. There it is. And now you'll notice I also have this horizontal line at y equals 2 right here. And so this is the area that we're looking at. And we want to revolve around the y-axis. So I'll draw in a little rectangle right here with a delta y. All right, so notice now we need to swap our function around. If y is equal to the square root of x, then x is equal to y squared, right? And we can make sure that, yep, both are positive, so everything's going to be fine in this case. If we had different signs going on, we'd have to be a little bit tricky about things, but no big deal. All right, so x is equal to y squared. That's the function that we're going to be looking at. See if you can set this thing up. Pause our video, see what happens. When we come back, I'll help draw out some more things, our little cross section, and then we'll go from there. Okay, but actually pause the video. In my normal classes, I would tell everybody to talk with each other and work on some stuff by themselves and things like that. So actually do it. All right, hopefully you've done that. If not, again, pause and go ahead and do it. All right, so here's our little cross section. It's this nice circle. Our radius now is this distance, which is actually y squared. So there's our radius. Our area then is going to be pi y to the 4. So our volume is the integral. I'll take my pi out front. Y squared squared, so this is y to the 4 dy. My limits of integration are the y values from 0 to 2. So again, this should be a pretty easy thing for us to do. Pi times y to the 5th over 5 evaluated from 0 to 2. That's pi times 2 to the 5th. What's that, 32 over 5? So we'll call this 32 pi over 5. No big deal. So when we do things with regard to the y-axis here, revolving around the y-axis, we have to swap our variables around when we're using this disk method, just to make sure that we're integrating with respect to the correct variable. Notice you can always tell what variable you're integrating with regard to if you draw a rectangle and draw your little delta x or delta y on the small side of your rectangle. That's going to tell you what your differential in your integral needs to be, and so that'll help you figure out what variable you need to be using as your input on the function. All right, we have one more thing to introduce. It's called the washer method, and really it's the same thing as the disk method. It just adds a little bit more complication. So what we're going to do is we're going to add a second region to our setup that we have. So we had that square root function. I'll draw that in green again. It's still between 0 and 4. But now what we're going to do, I'll draw this in red, is we're going to have the function x over 2, which is a linear function that goes between these 2 points. It crosses also at the point 4, 2 and 0, 0 conveniently. So this is the area we're looking at for our region, and what we want to do is revolve that thing around our y-axis, or x-axis, sorry. All right, so let me see if I can sketch what this will look like. It's kind of tricky to sketch things, especially because I am notoriously bad at sketching stuff. But oh well, I'll do my best. So here's our little cup shape that we saw, but then we also end up with this kind of weird hollowed out wedge. You can think that what we really have is like that cup minus a little conical bit that we pulled out, and these things are around here. I don't know if this is helpful or not to see, but hopefully we can see a little bit about what's going on here. And now we want to find the volume of this thing. So what we need to think about is our cross sections. I'm going to draw my rectangle, and you'll notice now it goes from a top function to a bottom function. I still have a little delta x, which is good. But now when I revolve this around my x-axis, it's going to create this shape right here. It's going to be connected this way. Oh boy, I'm having a hard time drawing this. I should have used some dotted lines. Oh well. So what you'll notice is that when we do it, I'll draw it out here and it'll be easier to see. We're going to have this little washer. If you don't know what a washer is sometimes used as like a spacer with bolts. Sometimes it's used for distributing some pressure and stuff like that that's added. You can essentially think of this as like a flat donut. I prefer to think of them that way. So what we need to do now is find the volume of this thing. Well, the volume of this shape is just going to be the area of the face times the thickness, and the thickness is still delta x. So let's go ahead and draw the face of it. We've got this circle, and then we've got this circle. So we need to come up with the area of this, and that's not hard, because this is just a circle minus a circle, right? We have some small radius, and we have some big radius, and if we can find the area of the big circle, we'll subtract the area of the small circle from that, and that should work out fine. So our area function is going to be, I'll call this one R1 and R2. It's going to be pi R2 squared minus pi R1 squared. Maybe I should use B's and S's for big and small, but whatever. All right, so now we got to figure out what is R1 and R2. Well, on our picture, hopefully we can see that this distance is the big radius. It's the distance from our axis of revolution to the very outer edge. And that's our function f of x, our square root. And this distance here is our small radius. Notice that's just the distance from 0 up to this red function. That's x over 2. So our area function really becomes pi times the square root of x squared minus pi times x over 2 squared, or pi times x minus x squared over 4. Our integral then is going to be pi, I'm going to give myself a little bit of space, pi times the integral, again from 0 to 4, those are my limits of integration because those are the x values bounding us, of x minus x squared over 4 dx. Polynomial function should be easy enough to integrate. I'll let you go ahead and do that. So let's just kind of summarize the washer method here. The washer method says that if you have two functions like this, where f of x is greater than g of x. They're both continuous. Then when we look at the area bounded between those things and revolve it around the x-axis, then we just have to make sure we subtract the area of that inner part. What happens when it's revolved around the y-axis? Exactly the same thing. And so we end up with a volume from C up to D of, I'll bring the pi out front, and what we would have is f of y squared minus g of y squared dy. And again, in this case, we're not necessarily thinking of top and bottom. We're thinking of the rightmost output x value versus the leftmost x value. Whereas in this case, when we're talking about y values, that is a top function. That is a bottom function. This acts a lot like area between curves, except now we're squaring these functions because remember, they're acting as a radius of a circle that we're finding the area of. So that's what we've got for the washer method. Big question, how can you tell whether you use disks and washers? And there are a couple of key points. First is that washers typically have a couple of functions being listed in here. We need to know what that inner radius is, right? We have two functions, f and g. And for disks, we didn't have that. What you could think is that for disks, your inner radius, the small radius or function, is just 0. So what you'll notice is that in this sense, our region runs right up against our axis of revolution because that inner radius is constant at 0. Whereas with washers, that region does not bump up against the axis of revolution because there's some other function bounding it before we get there. So just keep an eye on that. That should hopefully be a helpful way of distinguishing between